very deep problem. It's a very important problem for me, and I know now which my result is excellent, which my result is good, which my result is bad. If I can see my result, therefore this result is excellent. Yes, in India, good result you can see. Yes. If I cannot see, then result is bad. I had today a lot of speech, a lot of talk, and I had a lot of songs today. And I try to give you my song. And I start from Dynamical Systems. Approximately in 1850, number theory was the result. Declared and proved two excellent results. Declared proved for every alpha, L alpha is the equality. First solution for every Q and Q small between 1 and Q big. And we will prove that if alpha is algebraic, degree of alpha is L, and then we have for every rational point alpha minus P over Q, and here C of alpha Q to power n is the degree of alpha. And as usually we use very trivial but very if alpha, we have integer number, then for some m over q less than alpha, and m plus 1 over q greater than alpha. I can take p m or m plus 1, and here alpha less q squared per q. You can see that this inequality is the best possible, because if alpha is the middle of this interval, then we have here equality. But we have here 1 over 2q, and here 1 over q squared. This is much more stronger. We have excellent approximation by small Dasher numbers q. And we can take now gamma 1 alpha, gamma 10 to power factorial, and it's not so difficult. It's easy to prove that gamma is transcendental number. Therefore, we have transcendental number. If here we can take an integer between, we can construct uncountable sets of transcendental numbers. It was only 1950, more than 1.5 century ago. Excellent result. But Unfortunately, we know not so many about irrational numbers. Today we don't know e plus pi belongs to the set of rational numbers or not. Second, gamma, number of Euler number or zeta in the point to n plus 1. Sum in 1978, Abiri proved that this number is irrational if n equals 1. But nobody knows that the structure of this number when n is of course integer and greater than 1. If this power 5, nobody knows answer. Therefore, we about solution of this inequality. We know not so many. If we take alpha, then nobody knows answer about alpha minus p over q, less perhaps q minus 2, so on. Alan Baker proved that inequality q minus, if q greater than q0, and I know the result is here 2 minus 2, and I don't know exactly recent last result is this picture. And we know approximately. We know 88 yes. That engine theory. For every if L1 over psi is the set of alpha from some interval, is for which inequality 1 holds infinity often. And psi of q is monotonic, and tends to 0. Psi of q tends to 0 monotonically. Then the measure, Lebesgue measure of this set equal 0, or the length of interval measure of interval. It depends. Side of Q. Here, convergence. And here, the same series. Divergence. And we know well that convergence and divergence sometimes absolutely the same. Yes? It is a joke, of course. If side of Q equals Q minus 1, minus 1, $2,013 times logarithm. And gamma, it depends from gamma. If gamma less or equal 1, the series divergence. If gamma greater than 1, then the series converges. But please,
minus
it was not joke. Therefore, please calculate this function for gamma equals half and for gamma equal 2. Absolutely the same result. Yes? And therefore, Hinch's theorem will give us excellent result. I can Hinch's theorem give us excellent result. I can because it's serious. Excellent. And now before Hinch's theorem, there was theorem of Baroda. in 1890 and 8 proved this theorem for here Q minus C. And now there are a lot of unsolved problems about rational approximation of real numbers. But we can answer on the question about approximation in majority cases. And I want to tell you that the problem there are a few unsolved problems about approximations by rational numbers. Much more difficult. The problem about approximation of real and complex numbers by algebraic. Beta is the root of polynomial, irreducible polynomial. P of beta is 0 and degree of beta equal and if coefficients haven't common factor, then h of v beta equal h of polynomial maxima of modular of coefficients. And we have here the theorem as declared theorem. In 1960, Edmund Bernik proved if v less than n over n plus gamma 1 3 over 2, but it's not so essential for us. This inequality is equality 2 for every x, has infinitely many of solution of algebraic beta, degree of n, and height of beta, h. And nobody improved this. Therefore, we know a few about basic inequality. But for polynomial, if we have problem p of n of x, here psi of h, where psi is monotonic, tends to 0, and let psi be the set of real numbers for which inequality 3 has infinitely many solutions. And x belongs to some interval. Then the measure of this set and absolutely the same result. 0 and the length of interval. It depends on series n plus psi of h here and here 2 h equal 1 infinite, and here this series convergence and the same divergence. Therefore, we have absolutely the same result as Hinching for polynomial first degree. This result in this case convergence proved I, and 10 years later, Bernik
Can I ask a question? The n here is, sorry, the degree, you fix the degree?
fixed degree. Polynomial of fixed degree n. We fix degree and only h height of polynomial change.
But the theorem is valid for all degrees.
All degrees. All degrees. And in this case of convergence, I used special proof. I proved the result of Sprinchuk and Alan Becker, and Beresnevich improved result Alan Becker and Bolikon Schmidt about regular system. It's very important for this problem. This set. I don't understand what is the set of X for which this inequality is correct. But I have, it's very easy. C of n, C1 is easy to prove. If alpha 1 is the nearest root of polynomial p of x to x, then here p of x. And here, first derivative in the denominator of polynomial is the point alpha 1. And if the structure of this set is very easy, alpha, and interval alpha 1, and interval here, here the length of interval equal right hand side of inequality form. If alpha 1 is complex root, then the set is circle, and here the diameter of this circle, and here less than diameter. And we can work when the denominator is not big or not small. But the denominator can be very small. I know the best possible result. The denominator here is C2 H minus N plus 1 plus 2. But if N is big, then this estimate is better. And in before in the papers of Dani and Grigori Maguris, used for the defined approximation the method of dynamical system. Yes? Of dynamical systems. Dani and Magulis. After, on the basis of this result, Green box is taller than Dani. And the second. Used dynamical system for the solution of such problem. And AN here Fn of x. n plus 1 times differentials and Wronskian for first derivative f1, fn, and here f1 and derivative fn and derivative doesn't equal 0 for almost all x from interval. And then they prove principal conjecture that inequality fn of x less than h to power w if w greater than n infinitely often only for the set of zero measurements. And that basic, that my part of result, they can work with small values of derivative. And in our I can do when polynomial is small, but first derivative can be small too, but not so small as polynomial. But in result, in theorem of Kleinbach and Margulis, arbitrary. We have excellent Dirichlet and Jean principle. There are a lot of deep lessons for definite approximation, but almost all results give very primitive Jean principle of Dirichlet. And therefore, and it's for, if we take a polynomial, f of x, and here c0, and here u minus v0, here first derivative of x, c0, u minus v1, and arbitrary m of x, c0 minus b m and m plus g of x less than c0 when g between 1 and n minus. Then we can construct small pigeon in every direction. We have here n plus 1 direction. Some of them almost trivial, but n plus 1 not trivial. And some, and the value, if x belongs to interval, we can estimate the value of polynomial, the value of every derivative when h of p less than p. And then we can construct small boxes. And if every coefficient hg between 0 and q, we have, and for every fixed x, we just have a lot of points into this big Q. And if we take constant C0 and calculate the number of small boxes, then the number point will be greater. Yes. And there exists box with at least two the point. Then substitute these values, and this inequality is true. But in majority cases, this inequality if we put some fact, but very easy. From easy fact, we will have almost nothing. Yes. But if we take here absolutely the same, minus v m, and here q to power v0, and with small constant. And if one of this inequality doesn't true, there exists this theorem of Bernik. Bernik approximately that if B1 is a set of x for which this inequality is true, then there exists delta 0, C0, such that this system of inequalities is true, and x from I from interval, and measure of this set greater than 3/4 measure of interval. Therefore, for majority, I can take here the value arbitrarily close to 1, but less close than 1. Therefore, for majority, x, I can excellent situation. At the inequality right hand side almost equal left. Therefore, I have almost the bricks of the same size. It's very easy to build very big building if you have excellent bricks. And now I can, in this, from x to v1, I can take v0, vm, such that in neighborhood x, not far from x1, and here constant 2 minus mu. I can write the value of mu. It depends from m, but not so essential. I have a lot in neighborhood of x1. I have a lot. I have m L1 m-nodes of polynomial p close to x1. And then now a lot of last result. Majority of this result I put with last. Götze from Bernik, Bernik, York, Minsk, York. Now, and Minsk. And the last result, I put with Professor Piotr from Benefit. And two different cases. When the degree of polynomial be less or equal to n, or equal to n, and phi of p at most. And then for every polynomial, I take the root of polynomial and the nearest root, alpha 2 of p. And my first question is, for W1, I can find polynomial with very close roots. Of course, W1 greater than 0, and Q is big, tends to infinity. And there are a lot of papers, and this estimates W1 n over 4, n over 3, n over for general n, every n, Young Bujour plus co-authors prove that if n W1 greater than n over 4, then there exists polynomial for which is deterministic. Our result is the next. We can start we prove that there exist polynomials when W1 greater than n plus 1 over 3, and the cardinality of this set, this set with small roots, This is cardinality of this set plus additional condition. Cardinality greater than some constant C3, and here Q n plus 1 over 3. First result. Second result about discriminants of polynomial. For polynomial P, discriminant of P leading coefficients to power n 2, and here product alpha I minus alpha j when I begin on j n, and class P n of q b is P n of Q. For which discriminant of P less Q to power 2n minus 2 here and minus V, 2V. And I want to give estimates of Q. And we give lower bound here, and in first result, my first result is Cooksaw and Götze. When we between 0 and half, here is a number of polynomials, not polynomials, yes, number of the degrees of Q. And here the value of discriminant, D of Q. We wrote approximately 3 papers when we give a lower bound. And first result was approximately the same. Then here, straight line. This number curve, this curve consists of small intervals. And last result, I think close to final result, because for n equal 3, we can calculate the value of discriminant and give good upper bound and lower bound, and for n equal 3, our lower bound absolutely the same value as for n for our estimates for arbitrary n. For n equal 3, we put the same result. And last application. We take small in Q, big. Q is big. And interval I is small. And I ask you, can you construct algebraic alpha 1 degree of alpha 1 equal n? Alpha 1 belongs to I. For arbitrary n, can you construct polynomial with the root alpha 1? Exactly degree of alpha 1 equal n, and this root belongs to interval. And two answers. Answer 3, 1. Not if the length of interval half multiply. Therefore, if you take Q, I can take in